Lubricants and lubrication have played a key role in the advancement of machines and components over the centuries, from as long ago as 3,000 years, with the lubrication of chariots and water wheels, to current high-performance vehicles, heavy-duty transport, computer-controlled machinery, and space exploration. Regardless of the application, mechanical systems continue to depend on lubrication for efficient and durable operation. Lubricant developments have kept pace with the demanding requirements of our machines, working in tandem to properly lubricate those machines as they perform better, faster, and more precisely. To better understand how lubricants and equipment work together, we will focus on a few of the key requirements of lubrication, as well as the application and care of these lubricants. In the first chapter of this video, we will look at friction, lubrication, and wear, or the study of tribology as it is known. Next, we will examine the characteristics, formulation, and performance of fluids and greases. In the following chapter, you will hear about how oil cleanliness impacts these lubricants and how clean lubricants help you get the most from your equipment. Friction and the wear that results from friction are both important reasons for the widespread development and use of lubricants. Exactly what is friction, and why is it important? When an object is moved from rest, or when you continue moving an object that is already in motion, you find that you need to apply a force. This force is needed to overcome friction. If you don't supply this force, a moving object will slow down or stop. Whether we look at engines, the driveline components of a vehicle, hydraulic systems, gear drives, turbines, or the wide variety of greased applications, they all have one thing in common. Each has unique lubrication needs which require a lubricant tailored to reduce friction in that application. Lubricants provide performance well beyond reducing friction. Liquid lubricants can also provide cooling, corrosion protection, and remove particulate contaminants. Greases perform many of the same tasks while sealing out contaminants and reducing leakage. As you look at contacting parts on machinery, the surfaces look very smooth. The same parts, when viewed through a microscope, appear quite different. The microscopically rough surface is full of unevenness or asperities, which appear as peaks and valleys. The moving contact between these asperities results in friction when pressure is applied. The greater the contact between these asperities, the greater the friction and potential damage. In cases where high friction between metal surfaces exists without proper lubrication, micro-welding and micro-tearing can result, resulting in loss of efficiency and heat generation, as well as the creation of metal particle contamination in the fluid, which can further increase friction, wear, and damage. Frictional damage can produce a wide variety of wear effects. These wear effects are interpreted by lubricant and wear experts to uncover the source of the problem, which could relate to application, equipment, or lubricant issues. Gear tooth wear is a good example to show the typical types of wear seen by moving parts which slide or roll against each other. These failure modes are grouped into 4 categories: surface fatigue, wear, plastic flow, and breakage. Surface fatigue occurs when metals are subject to repetitive loading and unloading beyond their design stresses. This category of failure is subdivided into micropitting, pitting, and spalling. Micropitting is sometimes referred to as frosting due to the frosted appearance of the metal and is characterized by very small, shallow cavities, only 20 microns or less in depth, or about 1/4 the thickness of a human hair. Pitting consists of relatively small, irregular cavities on the metal surface from the breaking away of surface material. Pits have distinct edges and are typically larger than 20 microns. Some gear manufacturers consider a minor amount of pitting acceptable, as minor pitting is not generally considered particularly destructive. Spalling is severe pitting caused by subsurface metal failure, which produces larger cavities on the surface. Wear is different than fatigue, since it is related to the movement between two or more surfaces, where removal and deformation of material occurs. The two most common types of wear are adhesive and abrasive. Adhesive wear occurs where the pressure and heat of the contact between asperities on the metal surface come into contact with each other, and they adhere or bond to one another, displacing or removing metal as they come out of contact. Abrasive wear occurs between moving surfaces when hard particles dig into softer material. The hard particles are generated by either adhesive wear or solid contaminants. In such cases, the softer material will show abrasive wear as it loses material by the rubbing action of the harder material or contaminant. Scoring or scuffing results when metal from one surface under load is transferred to another surface under load and results in narrow and broad bands of tearing that are oriented in the same direction as the sliding movement of the parts. In severe cases, this displacement can result in the migration of material, resulting in plastic flow, where the contact surfaces will permanently deform due to heavy loads. The final and most dramatic failure mode is breakage, where part or all of a gear tooth fractures due to excessive load and gear stress. While we have used gears to demonstrate failure modes, similar failure modes exist for all contact between moving surfaces. In a machine, the lubricant is an important element in protecting parts from these negative effects of friction. Depending on the type of equipment, loads and operating speeds, different types of lubrication regimens provide this protection. This graph, known as the Strybeck curve, shows a plot of friction as it relates to viscosity, speed, and load. This graph is divided into 4 areas, which correspond to the 4 different lubrication regimes. From right to left, these are hydrodynamic lubrication, elastohydrodynamic lubrication, mixed lubrication, and boundary lubrication. These regimes relate to the lubricant film thickness in the contact area. Under hydrodynamic lubrication, the lubricant film is thick enough to completely separate the moving surfaces, minimizing friction. This type of lubrication is present under conditions of maximum lubricant film thickness and minimum load. However, fluid film lubrication fails under shock loading, low speed, high torque operation, or when operating with low lubricant viscosity. Under these high pressure conditions, the fluid film is squeezed out. As the interacting surfaces come closer together, friction increases along with pressure and temperature. The machine is now approaching the lubrication regime known as boundary lubrication. To prevent wear under boundary lubrication conditions, it's essential to use a lubricant containing anti-wear or extreme pressure additives. When activated by heat and pressure, these additives react with the metal surfaces to form a protective film. This film microscopically coats the surfaces of the metal components. The film has low shear strength and it acts as a sacrificial wear layer, reducing friction between the moving components and protecting them from excessive wear. Another type of lubrication, mixed film lubrication, combines the properties of fluid film and boundary lubrications, employing both a continuous lubricating film and a layered film to protect interacting surfaces. A special kind of lubrication, elastohydrodynamic lubrication, or EHD, applies to conditions of extreme high contact pressures. 2 things happen in EHD lubrication. First, the surfaces of the contacting parts deform elastically, spreading the load over a wider area. Second, the viscosity of the lubricant momentarily increases dramatically, increasing its load-carrying ability in the contact zone. The combined effect is to trap a very thin but very dense oil film between the surfaces. As viscosity increases, sufficient hydrodynamic forces are generated to form a full fluid film and separate the surfaces. Mixed lubrication is a mixture of boundary and hydrodynamic lubrication. The lubricating film separates most of the surfaces, but the asperities can still make contact with each other. Let's shift our focus to the operating conditions, since lubricants are exposed to such a wide variety. These conditions can adversely affect lubricants and shorten their effectiveness and life. While selection of lubricant base oils and additives can enhance effectiveness and prolong life, these adverse conditions must be understood so they can be considered when choosing the best lubricant for an application. Factors that can accelerate wear and component failures include insufficient viscosity at operating temperature, lubricant contamination, and inadequate amounts and/or types of supplemental additives. Examples of supplemental additives are anti-wear, extreme pressure additives, and friction modifiers that are used to augment or alter lubricant properties for specific applications. Lubricant contamination by foreign matter, such as airborne dust, water, or in the case of engines, combustion byproducts, is an important cause of component wear or failure. Dust particles are highly abrasive and can abrade metal surfaces much like sandpaper. Water is a potential contaminant in both engines and industrial lubricants. Water is a byproduct of the combustion process in engines and can condense from humidity in the air in industrial applications. In the presence of air, water or moisture can promote oxidation and corrosion, leading to rust of unprotected metal surfaces. The byproducts of combustion produced by engines, such as soot and other particulates, can also contaminate the lubricant, causing abrasive wear, lubricant thickening, and clogging of oil passageways. Lubricant contamination by liquids other than water can also cause undesired effects, such as the lowering of viscosity by fuel contamination in engines, and the altering of viscosity and lubricant characteristics when two incompatible lubricants are mixed. Contamination with another oil which has too low or too high a viscosity can change the overall fluid viscosity and affect proper lubrication, resulting in premature wear if too low, or generation of heat due to fluid friction if too high, which can lead to shortened life and increased deposits. With some lubricant mixtures, incompatible additives can combine with each other, neutralizing the benefits of the additive and plating out on parts or the filter. Oil and air filters or breather filters and their maintenance are critical in any lubricated system. These filters can capture airborne or suspended particulates in the air or fluid before they can cause serious damage to your equipment. It is important to keep these filters maintained, since they can prolong equipment life as well as fluid life when maintained properly. This maintenance is even more critical in very dusty or wet environments. We will discuss oil cleanliness in a bit more detail later in this video. While many lubricants may appear very similar to one another in general appearance and viscosity, they should be used only if they are the correct viscosity and meet the correct manufacturer's specifications. Using lubricants in applications for which they were not formulated, engine oils in a gear application as an example, can cause premature wear on the gears and can lead to early failure. While viscosity is the most important characteristic of any lubricating fluid, the performance profile must properly match the application in modern machinery, if you want long service life from both the equipment and oil. A viscosity change of 10% or more to a lighter or heavier viscosity can have a significant impact on many applications. Correct formulation balance with proper additive chemistry can be equally important. In this chapter, you saw that there are several physical processes at work which have a direct impact on lubrication, the most important of which is friction. We summarize some of the causes and resulting effects of friction, the different lubrication regimes, as well as how solid and liquid contaminants can degrade proper lubrication. Understanding these processes provides a good basis for further exploring the role of lubricating base oils and additives. Mineral oil alone lacks the performance characteristics necessary for protecting today's machinery and vehicle components. In this chapter, we will review how base oils and additives, which are properly formulated and balanced, provide the required lubricant performance and longevity which allow equipment to perform to their maximum potential. We will also discuss the viscosity classification systems and briefly compare the most widely used systems. Original equipment manufacturers and dedicated industry associations outline the needed performance requirements and may even monitor and issue approved listings of lubricants which they have reviewed or tested for use in their equipment. To meet these various requirements, oil companies select the appropriate base oils, then blend specific additives to achieve the desired performance for the application and operating conditions. Base oils are divided into 5 groups, which are specified by the American Petroleum Institute, or API. Each group has distinctive characteristics which include saturates, sulfur, and viscosity index. These characteristics help to segregate one type of base fluid from the next, as shown in this chart. Saturates refer to the extent to which the fluid has single bonds. Unsaturated hydrocarbons have one or more double bonds between carbon atoms. Sulfur refers to the sulfur content of the base oil. Viscosity index refers to the change of viscosity with temperature. The higher the number, the less the viscosity will change over a range of temperatures. Group 1 oils are manufactured by solvent extraction, solvent or catalytic dewaxing, and hydrofinishing processes. Group 1 base stocks contain less than 90% saturates and or greater than 0.03% sulfur and have viscosity index greater than or equal to 80 and less than 120. Group 2 base stocks contain greater than or equal to 90% saturates and less than or equal to 0.03% sulfur and have viscosity index greater than or equal to 80 and less than 120. Group 3 oils are manufactured by special processes such as severe hydroprocessing, which is treatment of the base stock with hydrogen under high pressures and temperatures. Group 3 base stocks contain greater than or equal to 90% saturates and less than or equal to 0.03% sulfur and have viscosity index greater than or equal to 120. Group 4 oils are POW or polyalpha olefin base oils. Group 5 oils include all other base oils, which include esters, naphthenic, polyalkylene glycols, and all other not defined by groups 1 through 4. Additive types used in oils include antioxidants and other inhibitors, anti-wear agents, extreme pressure agents, viscosity modifiers, detergents, and dispersants. Antioxidants, also known as oxidation inhibitors, reduce the ability of oxygen to react with the base oil. This minimizes oil breakdown and subsequent thickening. Oxidation occurs more rapidly as the oil is heated in any system and comes in contact with air. The more effective an oil is at resisting oxidation, the longer it can maintain basic lubricating characteristics and resist deterioration. A good, generally accepted rule of thumb can be used to show the effects of oxidation. For every 10 degrees Celsius or 18 degrees Fahrenheit increase in operating temperature above 75 degrees Celsius or 167 degrees Fahrenheit, the oxidation rate of an unprotected lubricant almost doubles. Antioxidants work either by reacting with unstable oxidation products or by decomposing peroxides in the oil. Oil thickened by oxidation can cause bearing failure if the oil pump cannot maintain a sufficient flow, and it can plug filters and find passages needed for even distribution of lubricant in many lubricating systems. Oxidized oil contains acids which can corrode metal surfaces. Antioxidants are found in almost every lubricant. Other inhibitors protect against rust and other types of corrosion caused by the attack of oxygen and acidic byproducts on metal surfaces. Rust or iron oxide, typically occurs when unprotected iron alloys are in the presence of water and oxygen. Rust and rust particles tend to degrade surface finishes and clearances, causing contact surfaces to change, wear patterns to alter dramatically, and significantly shorten the life of the equipment. Rust and corrosion inhibitors work by forming a protective film on the metal surface. This film acts as a barrier, stopping or at least slowing the development of the rust. Other corrosion inhibitors may work to neutralize the corrosive agent. Rust and other corrosion inhibitors are used in almost every lubricant. Anti-foam agents, or foam inhibitors, eliminate lubricant foaming, caused when the rapid mechanical action of parts creates air bubbles in the oil. These bubbles are called entrained air when they are below the surface of the fluid, and foam above the surface of the fluid. While some foaming in very active systems is sometimes considered normal, foaming is generally not desirable. Foam inhibitors break the surface tension of the bubbles, allowing the bubble to burst. Polymeric silicone compounds are normally used as foam inhibitors in engine and transmission oils. These silicone compounds are not oil-soluble, but rather are in fine suspension within the oil. Polymeric ester foam inhibitors are usually used in gear oils and are somewhat oil-soluble. Foam inhibitors are commonly used in most formulations. Anti-wear agents are additives which react with the surface of the metal to reduce metal loss by reducing or preventing metal-to-metal contact. They typically include boundary film-forming phosphorus compounds such as zinc dithiophosphates. Extreme pressure agents are a different type of film-forming phosphorus additives, such as sulfur phosphorus compounds, used under extreme loads, low speed, and high temperatures, such as gear applications. Both anti-wear and extreme pressure agents function similarly, with chemistry and severity of application being the main differences. Anti-wear agents are typically found in everything from hydraulic oils to engine oils. Extreme pressure additives are typically found in gear oils. Viscosity index improvers, also known as viscosity modifiers, help maintain a more stable lubricant viscosity across a wider range of temperatures. These viscosity modifiers are oil-soluble organic polymers which thicken oil viscosity at high temperatures. At low temperatures, where a relatively lower viscosity is more desirable, the dissolved molecules occupy a small volume in the bulk oil. At higher temperatures, the polymer chains expand, occupying a relatively larger volume in a given quantity of oil. This increase in the relative size due to the expanded surface area slows the movement of the molecules inside the fluid, changing the apparent viscosity of the fluid. Many different kinds of viscosity index improvers are used in everything from engine oils to gear and hydraulic oils. Pour-point depressants allow oils to remain fluid at colder temperatures than normal by controlling wax crystal formation at low temperatures. Pour-point depressants function by interrupting wax crystal matrix growth. By keeping the wax crystal size smaller, the lubricant remains fluid at colder temperatures. This is critically important in circulating systems with filters, as crystal formation can block or plug filter elements at lower temperatures, potentially starving equipment of lubricant and shortening component and equipment life. Detergents protect parts against carbon and varnish buildup, which is vital for parts with close clearance such as piston rings and skirts, valve lifters and oil pump relief valves. Detergents prevent contaminants from adhering to component surfaces and neutralize the acidic or corrosive effects of oxidation or combustion byproducts. Modern detergents are primarily metallic salts, such as calcium sulfonate or magnesium sulfonate or mixtures of the two. Detergents are used mainly in engine oils, with some use in transmission fluids. Dispersants minimize the tendency of contaminants to clump together or agglomerate into larger particles, which may settle out as varnish or sludge in different applications. Dispersants are non-metallic additive chemistry. While dispersants have traditionally been used only in engine oils, they are finding wider use in some industrial fluids where varnish is a growing issue. Other additive chemistries which are used in specific lubricants include emulsifiers, demulsifiers, friction modifiers, metal deactivators, and dyes. Demulsifiers and emulsifiers modify the way the oil and water react. Emulsifiers allow two ordinarily immiscible fluids to form a stable emulsion. Emulsifiers are usually added to lubricants containing a high concentration of water, such as soluble metalworking fluids, to keep the water and oil from separating. Demulsifiers speed the separation of water from the oil. Demulsifiers are typically found in turbine oils and other circulating oils where rapid separation of oil and water are desirable, to avoid circulation of any water and oil mixture on contact areas, such as bearings. Friction modifiers perform two different functions depending on the application. In engines and way oils, they reduce friction, which improves operating efficiency, reduces heat, minimizes wear, and decreases noise. In automatic transmission, tractor fluids, and industrial applications with clutches, they increase dynamic friction or decrease static friction to control power transfer between clutch plates, decreasing chatter, heat, and wear. These compounds absorb or attach themselves onto the metal surface, where they reduce friction at the lubricant-metal interface, leading to improved operating efficiency. Metal deactivators protect yellow metals such as copper, brass, and bronze from corrosion by forming a protective film on the surface of the metals that are in contact with the oil. By doing this, they protect these metals from acting as a catalyst in the oxidation process, as well as from certain additives which may be more chemically active towards these softer metals. Metal deactivators are sometimes used in cooling systems with copper or in equipment with copper or yellow metal components. Finally, dyes are used to permanently change the color of lubricants to enable the easy identification for users. This is most commonly used where consumers may misidentify lubricants, causing severe damage to equipment from the misidentification. Color-coding lubricants has proven effective at reducing this risk. Typical color identification includes the use of red dye in automatic transmission fluid and purple or blue for two-stroke engine oil. In this chapter, we discuss that lubricating fluids are a blend of a variety of base oils and any number of different additives. The type and amount of the base oils and additive is determined by the viscosity and performance requirements of the equipment and the specific operating environment. In Chapter 1, we discuss the importance of viscosity. Let's take a closer look at various viscosity classification systems used in transportation and industrial applications, and how they compare to one another. Several industry organizations are involved in various viscosity classification systems used by transport and industry. They include the International Standards Organization, ISO, the Society of Automotive Engineers, or SAE, the American Gear Manufacturers Association, or AGMA. All of these viscosity classification systems now use centistoke as the standard unit of viscosity measurement. If we review the ISO viscosity grade system, a few important facts stand out. The ISO viscosity grade system is reported as the viscosity in centistokes at 40 degrees Celsius. The ISO viscosity grades are reported at regular intervals, with the limit of plus or minus 10% from the midpoint viscosity. On review of the AGMA viscosity grade system, you can see the similarity to the ISO viscosity grade system, with the key difference of the use of sequential numbers instead of viscosity midpoints. As we compare the SAE crankcase viscosity grade system, a comparative temperature at 100 degrees Celsius must be used, which is much closer to actual application temperatures than 40 degrees Celsius. The SAE crankcase viscosity grade system also includes cold temperature performance and shear characteristics, which are not taken into account on this chart. The SAE gear viscosity grade system is similar to the SAE engine viscosity grade system, except that different cold temperature testing is included. As you can see by this chart, there are definite similarities between the different viscosity grade systems, but with critical differences between transport and industry applications. It is important to remember that lubricants are carefully formulated and chemically balanced fluids, designed for specific purposes and unique performance features. There are many applications where fluids may not be the best choice for the application, since gravity, or centrifugal action, may either push too much lubricant into the contact area or keep it from the contact area. In this case, a thickener can be added to give the desired characteristics, which will be discussed in the next chapter on greases. Grease is generally defined as a semi-solid liquid. For the purpose of lubrication, most lubricating greases are better described as a dispersion of a lubricating oil in a soap or thickener. Greases have the unusual characteristic of being very viscous or thick until shearing is applied in an application such as a rolling element bearing. Under shear, the grease reduces viscosity to an effective viscosity very near that of the oil dispersed in the thickener. This action is called thixotropy, and is the reason greases can also be referred to as thixotropic greases. Greases provide a seal or barrier which is inexpensive and can be easily reapplied by users to purge and keep out contamination. The fundamental difference between lubricating oils and lubricating greases is the thickener and the ability of grease to suspend special solid lubricants and other beneficial additives which are not soluble in most lubricating fluids. Another key difference is the ability for grease to stay where it is applied and not pool like a liquid. We will cover two main topics in this chapter: the National Lubricating Grease Institute classification system and some of the special additives you may encounter in greases. In order to better classify, the National Lubricating Grease Institute, or NLGI classification system, defines 9 consistency numbers, or NLGI grades, which relate to the softness or firmness of a grease. Most lubricating greases used today have between a soft and firm consistency of an NLGI 1, 2, or 3, as shown on this chart. The testing of consistency is fairly simple. The grease to be tested is brought to a standard temperature and worked in a device called a grease worker. A sufficient sample of this grease is then filled and leveled in the test cup. This consistency is then measured by a penetrometer, which measures the penetration or depth of a weighted cone in tenths of a millimeter into a container of worked grease at a given temperature in a specific period of time. The NLGI classification system chart gives the parameters of the different consistencies based on the results of the penetrometer test. Since grease thickeners have the special characteristic of being able to disperse, this allows them to carry non-soluble or solid additives like molybdenum disulfide, or moly, and graphite. With these additives, grease has the potential to provide benefits for special lubricant applications where liquid lubricants do not provide sufficient friction reduction to prevent wear. These type greases are typically found in mining applications, fifth wheels, and similar applications where the equipment operation does not replenish the grease during normal operation. It is important that the size of these solid additives particles is sufficiently small and uniform to provide metal-to-metal separation without causing particulate damage. Most other additives found in liquid lubricants are also found in greases, imparting other special properties such as special tackiness, water wash-off resistance, wear and oxidation resistance, and dyes to add color for application identification. There are many facets of grease application and testing which are unique and can be examined separately. We have reviewed the fundamentals of the basic formulation and performance characteristics of lubricating fluids and greases in the past 2 chapters. Before concluding, there is one last but very important area we should review: the cleanliness of lubricating fluids. In the first chapter, we discussed contaminants that can cause wear. In this next chapter, we will take a closer look at the importance of filtration and fluid cleanliness. The purpose of an oil filter in any circulating system is to remove impurities to prevent them from continuing to circulate and damage the equipment components mentioned earlier. In this chapter, we will examine measurement of particle contamination, standard methods to categorize and count particles in fluids, and handling of lubricants to ensure cleanliness. Now that we can better understand why oils need to be kept clean from contaminants, let's take a closer look at the measurement of those contaminants. First, let's change our perspective. Many impactful contaminants have the potential of being much smaller than the width of a human hair. To give you a better perspective, the width of a human hair is about 0.075 millimeters or 75 microns. The unaided human eye cannot see items smaller than half of this, or about 30 to 40 microns. Compared to these measurements, fine and coarse wear particles are about 5 to 15 microns across, respectively. This may seem small, but not when compared to an oil film, which is on the order of 1 micron thick. Particulate analysis for lubricating fluids has become a standard tool for maintenance staff interested in keeping equipment running at peak performance. This is done through equipment-mounted, real-time particle sensors, portable testing units, and through routine oil analysis offered by oil analysis laboratories. The standard used to classify particles in a given sample of fluid is the International Standards Organization, or ISO, 4406-1999 standard. This standard utilizes a 3-number system to classify system cleanliness using a 3-tiered numbering system as shown here. The first number represents particles greater than 4 microns. The second represents particles greater than 6 microns, and the third represents those greater than 14 microns. As an example, a particle count which reports 22,340 particles per milliliter, which are larger than 4 microns, is expressed as 22, since 22,340 falls between 20,000 and 40,000. The same interpretation system is used for the particles larger than 6 microns and those larger than 14 microns, resulting in a reportable ISO cleanliness code of 221813. Component and equipment manufacturers will normally give guidance concerning the minimum fluid cleanliness desired to ensure long equipment life. Equipment manufacturers will include proper filtration media as part of the total equipment design. The best way to ensure a clean system and to minimize wear from particle contamination is to ensure new oil is clean before it is introduced into the equipment. Regardless of the starting oil cleanliness level from the drum or bulk tank, the use of potentially particle-laden transfer containers and devices can compromise the cleanliness of the oil during the transfer process. Use of a filtration cart with proper filtration cartridges to filter oil as it is pumped into equipment will ensure clean oil is being introduced into the system. In this video, we have covered a few of the fundamentals of lubrication. We have discussed the basics of friction, the function of lubricants, and the impact of wear. We have also discussed some interesting and important information about the characteristics, formulation, and performance of lubricating fluids and greases, as well as the importance of fluid cleanliness. Reduced maintenance, longer equipment life and energy efficiency are three of the more important factors that should be considered when choosing lubricants which meet the requirements of the equipment. As equipment manufacturers and operators identify new requirements and applications, Shell will continue to develop new lubrication technologies.